Okay, good morning, everyone. And we are going to start with true random number generators, as Ingrid mentioned in the previous talk. So the title that I came up actually this week for the presentation is Taming the Mess, a true random number generator design for secure hardware. Why this title? Well, because I think there is a lot of mess when you talk about true random number generators. Mess in terminology about what is a random number generators and what types of random number generators there are, how people divide them, but also the physical mess. Because when you think about it, you want your randomness to come from a messy process, something that is unpredictable to an attacker. So, first, where do we use randomness? Randomness is used in lottery. For example, in casinos. It is used for simulations or games. But it's also used in cryptography and hardware security. Randomness is also used in voting, which might sound weird, but if you remember, for the people who live in Belgium, in 2024, the order of the political parties on the voting ballot was determined by randomness. It was decided that innocent little kids are going to pick up the random balls from this big ball, and in that way determine unbiasedly the list of the order of the parties. Why do you want this to be decided as randomly as possible? Well, because studies from psychology have shown that the parties that are more in the top have higher chances to get votes from undecided voters. In this case, it was the idea was that by using randomness, this process is going to be somehow lessened. Okay, but we are not interested in voting here. We are here for cryptography and security. So, how big is the relation between crypto and randomness? For example, if you go to Google Scholar and you search for terms security and cryptography, you get around 1,130,000 results. If you add additional word, and that is random, you get 824,000 results. So that means that around 75% or 3/4 of the papers refer to randomness. So there is a strong connection between crypto and randomness. But this is already familiar to you because you have been following the talks the whole week here. Before we go into more details, we might ask ourselves, okay, randomness is important, but how important? What can go wrong if we do not use sufficiently good randomness? Well, remember Crane's talk from Monday? I think it was one of the first talks this week. And the RSA. So RSA security relies on the fact that it's very easy to multiply two large primes, but it's very difficult to factor large non-prime numbers. However, if you have, does the pointer work? Yes. However, if you have two large integers, n1 and n2, and they share a prime, let's say p, with a second prime q1 and q2 different, then you can use, you can find the greatest common divider of these two numbers, get the p, and get the private keys as explained in the talk on Monday. And these are real-world problems. Since already 2012, it has been discovered that a lot of TLS and SSH keys generated on embedded devices and headless devices have the problem of using low random number entropy to get the private keys. So that means that a lot of these devices are going to share the prime. So it is easy for an attacker to just find the greatest common divisor and get the common prime and break RSA security. Another maybe more recent and more impactful maybe for the general audience case has been, comes from the end of last year, when the US government seized around 127,000 bitcoins from the Lubian mining pool, mostly used by, let's say, criminals or enemies of the United States in China. The problem with the software that they used was that the random number generator to create the wallets, to create the keys and the seed phrases for the wallets was very flawed. Basically, there is only 32 bits that could be random. So what the US government did is they just went to all 232 keys to find all vulnerable wallets and seize them in this manner. This is estimated to be worth around $15 billion. So a bad random number generator can be a very, very costly mistake. But let's go back to the title of the talk, messy. And the first messy question is, what is a random number generator? This is a random number generator. It's a big tube, I think around 30 meters, with complicated physical devices at each end. What is else a random number generator? This device. This device has a small laser setup inside. We see that these two devices are quite different, and they are all random number generators. This is also a random number generator produced by a company that only makes random number generators, the so-called quantum random number generators. This is also a random number generator, a chip. You can see that this chip is much, much smaller than these big pipes. It's kind of confusing, no? This is also a random number generator, a software, a piece of software that runs so-called AES pseudo-random number generator. And finally, this is also a random number generator, a wall of lava lamps coming from Cloudflare. How the randomness is generated here is, well, they just take the photo of the lava wall lamps, hash them, and get the output. So, in the end, we can define random number generators very broadly as the systems or apparati that generate unpredictable and statistically well-behaving random outputs. What do we use random number generators for in security? Well, you saw already on Monday that we need our keys for secret key and public key cryptography to be as unpredictable as possible. This relies, of course, on the Kerckhoffs principle, which states that in a cryptographic system, everything should be assumed known to the attacker except the keys. So we rely heavily on the secrecy, on the unpredictability of the keys used in our cryptography. Random numbers are also used as initialization vectors in crypto protocols, but also as challenges in challenge response protocols, and as protection against side channel attacks. You will see in around 45 minutes, I think, when Benedict starts his talk, how and where you can use random numbers to protect against side channel attacks. In this talk, I want to focus on random number generators in electronic circuits. We can divide random number generators in electronic circuits into, roughly speaking, 3 categories. Again, this is a messy topic, and depending on whom you ask, they might go for a different way of division. First are pseudo-random number generators. Those are devices or programs that generate random numbers using cryptographic algorithms, and they rely heavily on the security of the underlying algorithms so that the attacker cannot guess the inner state, meaning, for example, the key if you use block cipher-based algorithms, or the internal state if you use hash-based algorithms. based on the output. So if the attacker sees the output, for example, of a PRNG, he should not be able to guess what the internal state of the random number generator is. On the other hand, once the internal state of a pseudo-random number generator is known to the attacker, no matter what crypto you use, you will not have security anymore. Another type of random number generator, and the type that is going to be focus of this talk, are true random number generators. True random number generators use physical processes that are considered random from nature to obtain truly unpredictable numbers. So in this case, unlike PRNGs, we don't have a state the attacker can break and guess the future numbers. And finally, we have hybrid random number generators, which basically are a combination of true random number generators and pseudo-random number generators. We will see in the end one example of this random number generator that a lot of you probably have on their laptops. So, let's start with the general structure of true random number generators. First thing is randomness source. That is where our mess actually comes from. This randomness source is usually some analog process, some analog signal. Then we use the so-called digitization to turn this analog signal into usable bits, because we work in digital electronics and we are interested in digital bits to apply them for our crypto purposes, right? Then, as output, we get raw numbers. I call this somewhat tamed mess because raw numbers can be already usable for a cryptographic security, but not always. To make them usable for crypto and security, you would usually apply post-processing to improve the statistical quality, to improve the unpredictability of the numbers. Those numbers are then called internal numbers. I know it's a bit confusing because internal numbers, but they are the final output. Well, they're called internal because they're going to be then used internally by the crypto application. And that's what I call here the tamed mess. So finally, we got something usable, something that we can use for our crypto and security applications. And finally, we have on-the-fly or online tests. These tests are meant to test every process, every step of generation of random numbers to make sure that the unpredictability and the statistical quality stays at very high level. So, what are some design challenges when it comes to TRNGs? First, design of TRNG is inherently contrasted to the decades of work of digital circuit engineers who have worked on making circuits behave as reliable and as predictable as possible. When you make a TRNG, you want it to be reliable. You want your TRNG to always output random numbers of good quality, but you want it to be unpredictable. When you think about it, if you have an electronic circuit and you restart it, you always want it to behave in the same manner. You always want to get the same output. If this happens with TRNG, that's not a good TRNG. The other challenge is that TRNGs exploit analog sources of randomness in digital circuit, which sometimes can be very, very scarce. Third problem is the problem with tools. So modern CAD tools for functional verification and simulation are generally speaking inadequate to be used for TRNG design. Why? Well, when you design a circuit, you are always interested in the worst case behavior. What is the worst case noise? What is the worst case process variation? And so on. You're not interested what can happen in the best case, or when there is not enough noise, not enough process variations. And actually, that's where the randomness that TRNG going to use comes from these low noises and other unpredictable analog sources in circuits. Fourth challenge is that okay, now you have something maybe unpredictable, but you also want it to be reliable. You want it to be robust against voltage and temperature variations that might occur. One of the last problems is the so-called, the so-called my TRNG works, but I don't know why problem. That is, you design a circuit that you think is going to output random numbers, you test it, and indeed outputs random numbers, but when somebody asks you why it works, you do not know. And that's very, very fundamental issue in TRNG design, to know your circuit well and why it produces randomness. And finally, a very important question to answer is how much randomness is generated by every output of a TRNG. And to do that, we will introduce the concept of entropy. Entropy, very, very roughly speaking, we're going to define as a measure of disorder or unpredictability of a system. Entropy, and this is very important to remember, and what many people get wrong, is a characteristic of randomness generating process. It's a characteristic of a random variable. It's not a characteristic of a number or a bit sequence. Sometimes you will hear people, and even me, speaking about the entropy of a sequence, but whenever I say entropy of a sequence of entropy of a random number, I mean actually the unpredictability of the underlying randomness generating process. So first type of entropy that a lot of you, I think, might be familiar with is Shannon entropy. Shannon entropy is defined as average information content of the random variable. So it measures average unpredictability, and is given by the formula on the third line. Another important and even more important entropy is the so-called mean entropy, which is defined as a negative logarithm of the highest probability output. Why are we interested in mean entropy? Well, mean entropy is the most conservative unpredictability measure. It basically tells us the minimum amount of randomness introduced in our system by each TRNG output. And it answers a question, in the worst case scenario, how likely is an attacker to guess the RNG output on the first try? Well, you can just change the amount of entropy that you get in the formula here to the minus mean entropy, and you get the maximum, this probability. A simple example now, to see the difference between the Shannon entropy and mean entropy. Assume that we have a probability distribution of 4-bit output. So our random number generator outputs 4 bits. And with probability of 1/2, the output is going to be all zeros, while all other outputs from 1 to 15 will have equal probability. We now want to compute the Shannon entropy, and if you use the formula that is on the first line, you get something like 2.9534. So if you want to generate 128-bit key, you might need, I need only 44 samples, right? Because if you divide 128 with 2.95, you get around 44. But if you calculate the mean entropy, and mean entropy is very easy to see from here, mean entropy is 1, you'll see that actually you need 128 samples. And now I think it is very clear for you why the mean entropy is a better unpredictable measure than Shannon entropy. Because imagine if you use the Shannon entropy, then every time that you generate 4-bit output, there is 50% of chance that you will get all 0. Mean entropy is always conservative than Shannon entropy. Now, you might ask yourself, okay, what do I need to prove that my TRNG is working well? How can I test it? How can I prove to a user or to my cryptographic applications that my random numbers are unpredictable enough? You might think, well, passing some statistical test suits should be enough. We know, maybe you heard of different statistical test suits. So if you put your random numbers through statistical test suit and you get results that say, ah, yeah, this sequence seems unpredictable, maybe that's a good enough proof for my TRNG. Unfortunately, this does not confirm that a TRNG is a good TRNG. Many, even non-cryptographic based pseudo-random number generators are going to pass these tests. Another important thing that I mentioned on the previous slide is the mean entropy. We want to have a lower bound on the entropy, on the unpredictability that we get with each output of our TRNG. To solve this, we use a stochastic model. Stochastic model is basically a mathematical description of relevant properties of randomness or entropy source by using the random variables. A stochastic model consists of a family of probability distributions that is going to contain a true distribution of the random variable that is governing the randomness generating process in your TRNG device. It's important to say that stochastic model is not the same as a physical model because it is possible to model parts of your device that are only relevant for randomness generation, while for the other parts, you can just say those parts, even if they behave in the attacker-controlled manner, are not going to reduce the unpredictability, the entropy of my output. This stochastic model should be supported by engineering and physical arguments and probably also some literature findings. We saw that stochastic model is important for TRNG design, and that has been actually shown by the modern standards, methodologies, and certification authorities across the world. We have many different standards, but the three most important ones, and that modern TRNG designers want to be compliant with, are the German BSI, the document called AS31, which is basically de facto standard in Europe. And to fulfill common criteria, your design has to be compliant with this AS31 document, whose latest version came in 2024. So all these standards documents are updated from time to time. So if your design is compliant now, maybe in several years, people are going to put even harsher requirements, and your design will not be compliant anymore. So you need to follow up with the latest standards and recommendation. The second important standard is US NIST standard, so-called SP890B. This is a series of standards, SP890A, B, and C. So B is the one that concerns the true random number generators, or random bit generators, as they call them. This is a bit older document from 2018. It is getting updated. And the basic idea with the further update of both the German and the US document is to get them aligned as possible. They're quite aligned now. There are some inconsistencies, but the idea is to get them aligned so the designers, the future designers, be sure that once they become compliant with, for example, AS31, they're automatically compliant with SP890B and vice versa. And finally, in China, they have their own documents, GMT 005 from 2021, which defines similar requirements as NIST SP890B. So I said these documents are different. There are some common things, and the most important common things for you to remember from this talk is that they do not specify an approved TRNG design. So there is no AES version of a TRNG. There is nothing that you can say, this is compliant with NIST or with AES31, so I'm going to use that. So there is no single TRNG design that is specified as approved ones. Many different TRNG designs can be approved. Second important point that I mentioned is that a TRNG has to be unpredictable but reliable. I think it's already third time that I mentioned this, but it's very important. Third thing is that a TRNG has to be testable during the field operation. We saw in the general architecture of a TRNG that we have on-the-fly tests. These tests are here to test all the time whether our RNG is behaving as we want. And finally, very important is that these standards require stochastic model or statistical description and the lower bound on the mean entropy produced by each output of the TRNG. In that way, we can think that these standards tame the mess. They tame the terminology mess. Yes? Collision entropy is also used. Collision entropy is also used, but the standards also use mostly specify the mean entropy requirements. So that's why I wanted to only mention these types of entropy. I mean, there are many things that I did not mention in this talk because of the lack of time, but indeed the collision entropy is also used. Sorry. Yes. So Michiel asked about the usage of collision entropy in the TRNG design. Export control for key length?
Yes, there they are fine with collision.
I'm not familiar with that. I know that these, the standards for TRNGs, they mention collision entropy, but the final requirements is mentioned in the mean entropy. Actually, AS31 was using Shannon entropy until 2024. So you could claim the Shannon entropy. If the Shannon entropy is high enough, that was enough for this standard. Now, both BSI and NIST require mean entropy. The collision entropy is, it has its use, of course, but in these documents and for the certifications, yeah, not specified. Yes? Sorry? Would it be? Overkill. It is a good, because some people indeed argue that it is overkill, but it is, as I explained earlier, I think people want to be as conservative as possible with the RNG designs because the whole security relies on them. So people want really, really to be secure. So yeah, indeed, I also agree that in some cases they might be too conservative. As I said, standards do not approve the magic circuits, so the TRNGs that you don't know how behave, that you cannot describe well, that you cannot model well, but they require evidence for the randomness that they provide. Okay, let's go to the first part of the RNG design, and that is the entropy source. Remember, entropy source consists of two components. Those are randomness source, so our mass generating process, and digitization that converts this mass generating process, this analog signal, into digital bits. Another name for the entropy sources is physical entropy sources. Why I call them physical entropy sources and not just entropy sources is going to be clear by the end of the presentation, because we have something called non-physical entropy sources that some of you actually might be more familiar with than these designs here. So entropy sources generate raw bits, again, from unpredictable physical processes, and the raw bits might have biases, correlations, dependencies, or some other statistical flaws. Entropy sources, because they are based on the unpredictable physical processes, are very sensitive to operating conditions, so voltage, temperature variations. In this talk, I'm going to talk about 4 entropy sources. First is thermal noise on resistive elements, then metastability, timing jitter, and quantum effects in QRNGs. Again, this division can be said that it's a bit arbitrary, because some of the physical noise processes are parts of multiple entropy sources. And it's very important to say is that these 4 are not the only entropy sources. There are many, many more. First, thermal noise entropy source, and this was introduced by actually Intel already in 1999, and relies on the fact that you have two resistive elements let's say they are resistors. In actual integrated circuits, they're something else, but assume they're resistors. You will have some noise appearing on both of them. You will take the difference between them and amplify this difference. Why do you use the difference? Well, because these devices are not only influenced by thermal noise, but other noise sources as well. For example, noise sources coming from your power supply, or noise sources that influence the whole circuit. So you want to take the difference and extract only the part that is independent, and that is thermal noise. Now, this signal is then used to control voltage-controlled oscillator, which is then sampled by another high-speed oscillator to get a raw random bit. Now, if you are not familiar how the oscillators work, don't worry. We're going to talk about that in a couple of slides. But thermal noise TRNG is one of the first designs actually used in industry. The problem with this design, a big problem, is this analog noise. This analog noise amplification consumes a lot of power, and it does not scale well with new CMOS technologies. So when you go to the new CMOS technologies, you would have to do redesign again. Second entropy source that I want to explain is the metastability, or the randomness at decision boundary. These TRNGs basically use the fact that if you have two inverters connected back to back, and you power them on, they're going to be in the so-called metastable state, meaning that you will not know the output of this circuit until you turn it on. Once you turn it on, the circuit is going to be at this decision boundary, and then it's going to switch either to the so-called left or right. So you're going to have, for example, 0 here and 1 here, or 1 here and 0 here. This fact that the circuit is going to switch either to stable 0 or stable 1 is influenced by many different noise sources present at the time of powering on the circuit. And we come again with Intel TRNG, another design, so design that was introduced in 2012 in Ivy Bridge microarchitecture, and that is used in all Intel CPUs since then. So if you have an Intel CPU in your PC, you probably have this device. How does it work? Well, it's a quite complex circuit, but the most important parts are that we have two back-to-back inverters, as we saw before, and then we have feedback circuits. Why do we need these feedback circuits? Is we want, after we output one random number from this circuit, we want to tell our circuit, okay, we output this number. It could be that due to process variations, our circuit is inherently biased. So it is going to produce, if it produced 1 again, it's going to produce maybe 1 in the next time, in the next cycle as well. And you want to counteract, you want to fight the process variations, you want a reliable circuit. That's why they implemented this feedback circuit that when detects 1, it is going to load the other side of the circuit more with an array of capacitors and make that side stronger. So that side has higher probability to turn into 1 then. That means the other side will turn 0. What this creates, okay, you reduce now the bias, if there is a bias due to process variations, but it reduces correlations, right? Because if your output is 1, then we have circuit that is going to bias our metastability latch so that it outputs 0. So that means that 1, 0, 1, 0, 1, 0 is going to become very, very common sequence. To counteract that, you need some post-processing. We saw that post-processing is elementary part of the TRNG, and indeed, Intel TRNG does have mechanism to fight this, and we'll see it at the end of the presentation as well. Now we come to the most used entropy source, and that is the timing jitter of the elementary ring oscillator-based TRNG. So for you who have circuit background, this is quite easy. For other people, it might be not so intuitive. So the fact is that our delay, every circuit has a certain delay. In this example, we consider an inverter. This delay consists of, roughly speaking, very, very roughly speaking, two components. One is a deterministic component. Here is D0, and one is random components. This is delta D. This random component is going to be our timing jitter. Now we can connect multiple of these elements, inverters, in a so-called ring oscillator. So you put the output of one at output of one at the input of the next one, and so on until you make a loop. A loop has to have an odd number of inverting elements. You can make it either by having one inverting element, and all other elements in your circuit are going to be non-inverting, or you can use odd number of non-inverting circuits in total. So we have one ring oscillator, and then we have another ring oscillator that is going to be designed as closely as possible as the first one. The second ring oscillator is going to go to the frequency divider. What this means is that this frequency is going to be multiple times lower than the frequency of the first one. So if we look at the output here of ring oscillator 1, arrow 1 here, and if there is no random component, the output is going to look like this, like square waves. Because there is a random component, there is timing jitter, the output is going to be noisy. So on the edge, every time the signal goes from 0 to 1 or from 1 to 0, you're going to have some blur. You will have some non-determinism about the fact when does this timing occur. And this is precisely what we are going to use to get our random numbers. So if you imagine the red line to be the edge of the second ring oscillator, and that edge happens in this jittery zone, then if the edge happens before the rising edge, we are going to output 0. If it happens after the rising edge, we're going to output a 1. So what is the problem with this design? The problem is that the jitter accumulation is slow. I said earlier one of the design challenges is the fact that we use analog noise sources in our circuit design. That means that our output, the throughput of our RNG is also going to be slow, because we need to wait for the analog noise sources to become strong enough so we can reliably use them as sources of unpredictability. Another problem is that there are other noise sources that are autocorrelated or global noise sources, which also reduce the entropy, that also reduce the unpredictability of the produced bit by the design. So one idea to improve the throughput is to use multiple ring oscillators. So the idea is very basic. We just put multiple ring oscillator, we sample them at the same time, we XOR the output, and we get raw random bits. In that way, we can somehow increase the throughput of our design. There are other problems with this design, like think that these oscillators can become interlocked and so on, but I will not go into details here. The third example is the transient effect ring oscillator-based TRNG, which is very easy to understand. You basically have one loop, and you have even number of inverters. The idea is to introduce the edge into both parts of the loop, upper part and the lower part, and because you have even number of inverters, those edges will collide eventually. Then you can use the number of edges that have passed since the start of the circuit until collision as your raw random bit. And finally, we have quantum effect random numbers. I did not specify them in the separate category as QRNGs, because quantum effect random number generators, or QRNGs, are just type of true random number generators. The two most popular architectures are the photon beam split entropy source and light detector array entropy source. It is very easy to intuitively understand how they work, although their behavior is governed by the laws of quantum mechanics. So you usually have a source of light, usually laser, that emits individual photons. Those photons come to a 50-50 beam splitter, and each photon takes one of possible two paths. So it either goes through the beam splitter directly or reflects to another detector. We put two detectors at the output, and depending on which detector saw the photon, we are going to output 0 or 1. Ideally, this is a perfectly unbiased random number that you can use immediately for cryptographic applications. Unfortunately, the realities and non-idealities of the circuits impede that, right? Because your detectors are not going to be perfect. They will not always be able to catch photon. Sometimes they will see photon that does not exist. Your beam splitter is not actually going to be 50-50. It's going to be a bit biased. You cannot get perfect beam, and so on. There are many physical nuances here that make these raw random numbers actually not usable directly for cryptography, but again, you need to use some post-processing. The second type of quantum effect that I want to talk about is the lie detector arrays-based TRNGs or entropy sources. The idea is similar. Now, again, you have a source of light, but instead of using a beam splitter, you have just a big array of coupled detectors, of coupled lights that are going to detect that. Hopefully, one of them only is going to detect a photon, and the other one is not. And depending on which one detected, you're going to output 1 or 0. In this case, for example, you can say that the first one detected 1, and the second one, if there was no detection, you will say the output is valid, and you will output the raw random numbers. If there is an output in both detectors, so in both upper and the lower, we have this XOR circuit here that's going to say that the output is actually not valid, even though you have detected photons. So we now go to the post-processing part. I mentioned it already a couple of times. The goal of post-processing is actually to remove the bias, correlation, or other statistical imperfections in the raw random numbers and obtain internal random numbers that can be used for crypto applications. If it turns out that the entropy by the model of your entropy source is low, it cannot be used for security applications, it is important to compress the sequence that you get and obtain sequence that is going to have higher entropy rate. This is a very, very common mistake in TRNG papers, that they use post-processing techniques that actually are not compressing. Those techniques, like for example using a cryptographic hash function or block cipher, can indeed make your output pass the test and look nice, but actually you do not improve the entropy content, you do not improve the unpredictability if you do not do the compressing. We do the post-processing in two ways. First way is cryptographic post-processing. Those are using block ciphers and hash functions, which I think you heard about on Monday from Tim. And they provide computational security without necessarily increasing entropy per bit. As I said, if there is no compression, you cannot increase the unpredictability. You can increase the statistical properties, but you need compression in order to increase the entropy per bit. Those functions potentially have higher implementation costs if they are not readily available to your TRNG design, or they are used by other part of your crypto system. For example, you use a block cipher hash function for your crypto algorithm, but then you have to stop that and use it to hash and process your TRNG output. So you need to then make a decision. Either you're going to wait for the function to be available, or you're going to implement another one. Alternative is to use algorithmic post-processing methods. Those are non-crypto arithmetic methods that always increase the entropy density, so they're always compressing, and they provide information theoretical security. So they do not rely on the computational assumptions of the cryptographic post-processing. They usually are much cheaper to implement than cryptographic post-processing, but unlike cryptographic post-processing, they are usually designed to work only for a specific type of entropy sources. First example is the XOR post-processing. I'm going to explain how it works. It might be quite obvious for you, but for some people who do not have that background, I think it could be interesting to see how it behaves. So assume that we have a sequence here. We have some sequence of 16 bits. Then we take 2 bits, we XOR them together, and we get a 1. So if we XOR 1 and 0, we get 1. Then we move on to the second sequence of 2 bits. It's important that we move to another sequence, so we don't move 1 bit, we move 2 bits. We XOR them together. If we have 2 bits that are same, we get 0, and so on. We do this for the whole sequence, and we get the output of the XOR post-processing. Since we used only 2 bits in XORing process, we call this a 2-stage XOR. When we do XORing, it is important that the consecutive bits are independent. They can be biased, they can have different bias, but it's very important that they are independent in order for this post-processing to work. I said bias, but I did not define bias. Bias is very simply defined as the absolute difference between the probability of outputting 1 by your TRNG minus 0.5. When we apply XOR post-processing, let's say n-stage post-processing, we automatically reduce the throughput by a factor of n. And finally, we can use this formula here to calculate how biased our output is going to be. So if you use n-stage post-processing, our output bias is going to be 2 to the n minus 1 times the bias of the input sequence to the nth power. Important to note here is that the bias cannot be completely removed. It can be reduced as much as you like, but you cannot completely remove it. Alternative to using XOR post-processing is using the so-called linear correctors. Linear correctors came from the idea that I said before for the XOR post-processing, you should not overlap the sequences that you XOR together. But linear correctors actually allow you to do that. So how do they work? You have a sequence of raw random numbers, this one, and you have a matrix. This matrix is going to be a generator matrix of a linear code. So what you're going to do is you're going to take the first row of your matrix. You see where this matrix has ones. And at these places where this matrix has ones, you take those bits from your output and XOR them together. Then you move to the second line. Again, XOR together bits that the generator matrix of the linear code points to. So the key here is bits x1 and x3, and so on for the third row, where we have, in this example, bits 2 and 3 XORed together. Why they are nice is that if we have a minimum distance of a code and we say this distance is d, then we can easily calculate the output bias. But the problem is that these bits are not going to be independent. So we use XOR in a bit unconventional way to get better throughput, because remember now we combined bits from multiple places to get the output, but the bits to improve the bias. But the outputs now are not going to be independent. So you need to calculate actually the entropy of this sequence. So if you just rely on bias, you will get false sense of security because you indeed removed bias somehow, but you introduce some correlations. If you do these calculations properly, the formula is a bit complicated, I did not put it on the slide. You can see that actually you can use linear correctors in quite a nice way and improve throughput quite nicely with small problems with autocorrelations only. And the final post-processing that I want to talk about is the von Neumann post-processing. This post-processing works a bit not intuitively to many people. You take 2 bits, you again work pair by pair, and if they are different, you output the first bit. In this example, 1, 0, we output 1. Then you go to the next sequence, and if the 2 bits are the same, you do not output anything. There is no output from your post-processing. Then you move on, again 1, 1, no output, and so on. And you get something that looks like this. So you get bits by using von Neumann that are going to be completely unbiased. There will be 0 bias. However, the problem is that the bits here, in order to have 0 bias, need to be independent and identically distributed. Again, I said the bits need to be. Whenever I say bits need to be, I mean the entropy source that generated these bits. The problem with this design beside the fact that the bits need to be independently and identically distributed, which is another problem, is that the throughput is going to be significantly reduced. If you calculate, and it's actually very easy to calculate throughput, you can see that the throughput is always going to be at most only 25% of your original throughput. You get quite nice properties, so no bias, full entropy, full unpredictability, but you pay the price that the output is going to be significantly reduced. The more the sequence actually is biased, the more reduction in throughput you're going to have. Another issue with this design is that throughput is variable. As you can see in the sequence above, you will get your output at inconsistent times, and those times are unpredictable because you do not know what your TRNG is going to output, and that can be a nightmare for engineers designing systems that expect inputs at certain times. So you need to find a way to deal with this variable throughput. And finally, almost the end of my talk, is the topic of on-the-fly tests. I said on-the-fly tests, but I also want, before starting talking about on-the-fly tests, I want to say that we have something called prototype testing. This is testing that some of you might be familiar with, and that's the regular statistical tests. So you use familiar statistical test suits, like the test suits from NIST, SP822 or DieHard, and so on. You use long input sequences. They can be as high as 10 to the 9 number of bits, and you perform intensive computations in order to get the output and confirm the good statistical properties of your TRNG. However, these tests are computationally expensive, and they require a lot of bits. So they are not suitable to be used for the real-time detection of malfunctioning of our entropy source. On-the-fly tests are actually the tests that operate on the raw random bits, or possibly internal random bits. Remember, internal random bits after post-processing, to detect drops in the entropy or to detect drops in the statistical quality of the random bits. We have several types of tests here. The first are total failure tests. They're a very simple tests that immediately detect if your noise source is working or not. Remember the ring oscillator-based entropy source before. If your ring oscillator does not oscillate at all, you don't have zero entropy. So you need to implement a very simple circuit that is going to tell you whether the circuit works or not. This circuit is called total failure test. Then we have continuous tests. Those are statistical tests, but very computationally light, performed on the raw numbers that are going to tell the user about the quality of the numbers produced by the TRNG or entropy source. And finally, we have startup tests. Those are basically the same as continuous tests, but those are tests that are run every time your design is restarted to make sure that the restart operation has been performed well, and the numbers produced by these startup tests, used by these startup tests, are not going to be used in the application. So for the on-the-fly tests, we are both interested in the false positive and false negative rate. We have to decide whether we are going to go for the manual reset or we are going to go for the complete reset of the system, depending on the severity of the test. And what we aim for is that we have very small number of false positive during product lifetime, because we do not want to restart unnecessarily our TRNG if it's not necessary. The thing with continuous tests, as with many tests, is that they perform better on the longer sequence. This, of course, requires more usage and latency. And some standards, like NIST, specify minimum required tests that you need to run in order for your design to be compliant with these methodologies. There are three basic methodologies to design tests. The first one is stochastic-based methodology. In this case, you use the knowledge about the stochastic behavior of your entropy source to design tests. The second one are statistical black box tests. You apply tests like autocorrelation, bias, and so on, independently of the entropy source that you use, and those are the tests, for example, specified by NIST in their SP890B documents. And then you have the attack effects-based tests, methodology of making tests, where you expose your TRNG to certain attacks, measure the behavior of the tests of the TRNG during those attacks, and then make decision based on the output whether you're going to restart the design or not. I'm just going to briefly explain the attack effects-based methodology. The first thing that we want in this methodology is to define statistical features that we are interested in. So, for example, number of ones in a sequence is going to measure bias, autocorrelation, or frequency of some n-bit patterns. Then we want to design a false alarm rate. That is, we want to make sure that the tests do not, as infrequently as possible, say that there was attack when there was not attack. Finally, we want a metric called usefulness, which basically tells us how often attacks are detected. And finally, we want the tests to have a low hardware footprint. So how does this feature look like? For example, imagine you are measuring some feature, number of ones, for example, and as a golden reference, when your TRNG is not under attack, you get the distribution that is Gaussian, the yellow one. Then you perform some attack on your design, and then the distribution becomes red. So it deviates from the golden reference distribution. The usefulness is measured as the area under attack curve that is behind the upper and the lower bound designed based on the false alarm rate. So false alarm rate. So in this case, it is the area colored in blue. And to show the results of some case study, this is a case study done on the elementary ring oscillator TRNG. Here the attack is the so-called downsampling attack. So we want to sample the edge of the ring oscillator before enough jitter accumulated. Remember, these designs have the problem that they have limited throughput, that we have to wait for a long time for jitter to accumulate, and then we perform downsampling attack, so we sample the output before enough jitter is accumulated. In this case, 512-bit sequence have been considered, and the distribution of the number of ones in the sequence has been plotted here. So the black curve is the distribution under no attack, and the other curves, the dashed curves, are the distributions when there is attack. We see that we cannot reliably distinguish these distributions. So we go for another feature, and that is correlation. And in this case, actually, we see that the correlation feature is quite good feature because our golden reference, or a black distribution, is quite different from the distributions that you get when the design is under the attack. And finally, I want to say something about non-physical true random number generators. In this case, we have non-physical entropy sources, where the raw bits are generated from unpredictable but non-physical processes. Remember, I said the entropy sources is also something called physical entropy sources. Here, the entropy sources are non-physical processes, such as the system data or the movements of mouse, interrupt timings, and so on. Why are they called non-physical? Because we cannot build a good enough statistical model of these processes. Then these output are fed into so-called update function, which is often a cryptographic hash function or a PRNG, which mixes basically the entropy inputs from the non-physical entropy source to produce high entropy output. Then we have an entropy pool that the update function fills, and this is basically where we this is basically a memory or a register where we store the outputs. Then, when a user requires asks for the output, we take data from the entropy pool, we put it to the output function, which is again a hash, cryptographic hash or a block cipher, and we output it to our application. Again, we also have an entropy counter, which basically tells us how much entropy has been consumed by the application and how much entropy is left in the entropy pool. The good example of this, and why I said some of you might be familiar, is because this is something part of Linux dev random and dev random systems. And finally, we come to a full TRNG design, and that is the whole RNG architecture of the Intel's design. What it has entropy source, the metastability-based one. It has online tests. Those tests, the output of the random numbers of the entropy source are put to the AES-CBC MAC-based extractor. This is post-processing function to get the output, the so-called TRNG output of the Intel TRNG. So we have the whole chain of all the elements of the TRNG. Additionally, Intel implemented AES-CTR pseudo-random number generator, or deterministic random number deterministic bit generator, as it's called in the NIST, to satisfy the NIST requirements. Because NIST requires for your numbers not only to be coming from the true random number generator, but they need additionally to be processed by a PRNG. When you XOR the output from the PRNG and the TRNG, you get what they call the output of the TRNG, although this output is not direct output from TRNG, but is XORed from the output of AES CTR DRBG, and you can use the instruction RDC to get this output. Then you can also get directly the output of the PRNG, and that is so-called PRNG output. Note that you cannot get those two outputs from the same data. So you cannot get the PRNG and TRNG output, XOR them together, and get the output of the XOR. The system will not allow you to do that. So actually, you do not have access to the output of the TRNG in the Intel case. So what are the main takeaways from this talk? That the attackers may target the TRNG to attack instead of the underlying cryptography of the systems. TRNGs turn messy physics, remember the title of the talk, into something we can account for, into accountable entropy, accountable unpredictability. It's important to remember that the raw random numbers, just from the entropy source, are not always secure bits. They often require some post-processing. That the mean entropy estimation, together with the stochastic model and the on-fly tests, are always necessary to have in any TRNG for industry or practical applications. And finally, the post-processing is improving the output quality, but cannot create new entropy, it cannot create new unpredictability. And with this, I would like to finish my talk. If you have any questions, I can answer them.